we're going to be talking about boiling points, melting points, pure and impure. Okay, so how do we define the melting point? Now, the melting point is the temperature at which the solid becomes a liquid, but the solid and the liquid phase can coexist. Okay, so the melting point is when the solid becomes a liquid and the solid and liquid can coexist. Now, for pure substances, the melting point is a single number. A very narrow range. Maybe plus or minus 1 or 2 degrees. So for pure substances, the melting point will have a single number. It will be a very narrow range, maybe plus or minus 1 or 2 degrees. And for impure, the melting point will be a range, and it's usually lower than the melting point of the pure substance. So it's usually lower, so it's less than the melting point of pure substance. Now let's give an example. So for water, the boiling point is 100 and the melting point is 0 degrees. Now the freezing point is not equal to the melting point. So freezing is not equal to melting. It's not equal to melting. Now, for example, what happens if you add salt? So for example, if you add salt and you added 29.2 grams of salt, what happens is that the boiling point will increase. So the boiling point will now, so water plus salt, 29.2 grams, the boiling point will actually increase by 0.5 degrees. So the boiling point will now be 100.5 degrees, but the melting point will be lower. It will be lower by a certain amount. I can't remember by how much. But it is lowered. It is lowered by, let me find out, it is lowered. It is lowered by about 1.85 degrees. So it would be minus 1.85 minus 1.85 degrees C. All right, so let's just quickly recap. So the melting point is the temperature at which the solid becomes a liquid and the solid and the liquid can coexist. For pure substances, it will be a single number, but it can be a very narrow range. For example, it could be plus or minus 1 degrees. And for impure substances, the melting point will be a range, and it is usually lower than the melting point of the pure substance. So for example, water, the boiling point is 100 degrees Celsius, the melting point is 0 degrees. However, freezing point is not the same as the melting point. So what happens if you add salt to the water? So if you add salt, which is 29.2 grams of salt, the boiling point will increase and the melting point will decrease. All right, we're going to be talking about what happens when the change in temperature is very huge. So for example, if the boiling point of, well, we know the boiling point of water is 100 degrees. And let's just say that you've got 2 beakers of clear liquid. One of them is water and another one is something else. So if one of them was the boiling point, or let's just say you measure the boiling point of one of them is 100 and the other one is 170. So the one that is 170 will have a difference of 70 degrees. So therefore, the one that has the boiling point of 170 degrees would not be water. So if there's a big temperature change, it is very impure. Now, how would you heat a substance? First, you would heat it slowly. I mean, this is just to check the boiling point. So first, why would you heat it slowly? So then throughout the liquid or the substance, it is evenly spread out, and every particle in that substance will have its temperature increased, because you want to increase the temperature of the substance, but you don't want to do it too quickly, otherwise it will transfer energy to the surroundings. So you need to heat it slowly, so then the temperature increases evenly. And also you would need to stir, for example, if it was a liquid, you would need to stir the substance that you're heating. So then the temperature throughout the substance is the same, is constant throughout. And yes, and you don't want any huge temperature differences. So inside the substance, you don't want one area of the substance having a much higher temperature than another part of the substance. So you want the temperature to be uniform, to be the same. Okay, so let's do an example. So for example, let's put some solute into a solvent. Okay, let's talk about crystallization first. What is saturation? So if, let's just say salt or sugar. You put sugar into water or salt into sugar. In this case, let's just use salt. So you put the salt into the water, and the salt will dissolve in the solvent, and in this case it's water. So it will dissolve. However, if you put too much salt into the water, eventually the salt will not be able to be dissolved, because it's past the saturation point, because it just can't dissolve anymore. So if you put too much salt into the water, so you gradually add it in, gradually add it in more and more, eventually there'll be a point where you can't dissolve the salt inside the water. Okay, so why would the solubility increase as you increase the temperature? So you're putting energy into the substance, you're breaking the bonds, you're increasing the kinetic energy. So eventually the bonds will be broken, and then as the substances break apart, you'll be able to dissolve inside the spaces because you're breaking the bonds. So the bonds are broken, it is easier to dissolve in the solvent. This is assuming that the boiling point of the solute is higher than the boiling point of the solvent. Alright, we're going to talk about two different terms. The term here is filtrate and residue. So where do you think is the residue? Where do you think is the filtrate? So here you've got filter paper. Is the filtrate at the top, or is the residue at the top? So you know the filter paper, there are large gaps. And if you have large particles, then they can't go through the filter paper. Okay, so the substance that comes out of the filter paper is called the filtrate, and the solute, or the substances that can't go through the filter paper, will be called the residue. Alright, let's talk about the advantages of thin layer chromatography. Now, what's the difference between paper chromatography and thin layer chromatography? Now, a thin layer chromatography is where you separate non-volatile mixtures. Now, in paper chromatography, you use paper. However, for thin layer chromatography, you might use glass as the stationary phase, or plastic or aluminium. But let's just say you use glass. So in this case, thin layer chromatography, you can use glass plate with silica, that it will be the stationary phase. But the mobile phase, the one that gets absorbed through the stationary phase, the mobile phase will be absorbed by the stationary phase, and it will be the same as the paper chromatography. So the only difference is the stationary phase. What's the advantages of using thin layer chromatography? It is quicker, it is more sensitive, and there's a large range of stationary phases or solvents. Okay, so let's just do a quick recap then. So if there's a huge temperature change between the actual boiling point of a substance and the unknown substance, that means it is impure. Do you heat it slowly? Why? Because you want the temperature increase to be evenly spread out. And why do you stir? So then you want the temperature to be the same throughout the substance. And what is saturation? That is when the solute can't dissolve in the solvent anymore because there's too much of the solute. And why does the solubility increase? Because when you break the bonds, it is easier to dissolve. The filtrate is the substance that comes out of the filter paper, and the residue is the one that's left because they're too big to go through. And the advantages of thin layer chromatography is that it is quicker, more sensitive, and it has a large range of stationary phases or solvents. For further information, you can research colligative properties on why the boiling points will be different when you have different impure substances. Okay, let's have a look at this question. Z is a covalent substance. In an experiment, a sample of pure solid Z was continually heated for 11 minutes. So here we've got a graph. On the y-axis, we've got temperature measured in Celsius. On the x-axis, we've got time measured in minutes. So from 0 to about 2 minutes, it was about 80 degrees. And then from 2 minutes to 5 minutes, the temperature stayed the same. So therefore, there's a change of state. And then from 5 minutes to 9 minutes, so from 5 to 9 minutes, the temperature gradually increased. What is the melting point of pure Z? Okay, so if you look at the graph, you know that it starts off as a pure solid and then you're heating it up. So what's happening between 0 minutes and 2 minutes? Now, between 0 and 2 minutes, what you're doing is that because the heat is added to the substance, there's an increase in kinetic energy. So the kinetic energy is increasing inside the substance. Now look at that horizontal line. So this horizontal line, it's where there's a change of state, because the temperature isn't changing and all the energy is used to break the bonds. It's used to break the bonds in the solid. So once all the bonds have been broken, then it becomes a liquid, and that is when it's at 5 minutes. So the horizontal line tells you that the melting point is at 80 degrees. 80 degrees. Let's look at part B. The sample of pure Z began to boil at 9 minutes. It was boiled for 2 minutes. Use this information to sketch on a grid how the temperature of the sample of pure Z changed between 9 minutes and 11 minutes. Part C. The sample of pure Z was continually heated between 2 minutes and 5 minutes. Explain in terms of attractive forces why there was no increase in the temperature of the sample of pure Z between 2 minutes and 5 minutes. That's 2 marks. And part D, describe how the motion of particles of pure Z changed from 0 minutes to 2 minutes. Okay, so now it says, sketch on the grid how the temperature of the sample of pure Z changed between 9 minutes and 11 minutes. So because it says it boiled, it began to boil at 9 minutes. So that means that's the boiling point. So at 9 minutes, wherever it says I think that's around 220. So it says 220 degrees. Okay, so when it's at 9 minutes, the temperature is 220 degrees. So that is the boiling point. And because that's the boiling point, that is when it changes from a liquid to a gas. And so what you have, so the answer is, now you have a horizontal line from 9 minutes to 11 minutes because it is boiled for 2 minutes. So you want to draw a horizontal line from 9 minutes to 11 minutes. Okay, and now explain in terms of attractive forces why there was no increase in the temperature of the sample of pure Z between 2 minutes and 5 minutes. Number one, because there's a change of state, there's energy being put into the bonds. So the first mark you would say is that the energy is put to break the bonds or to overcome the attraction. And you've got to say between the molecules. So between the molecules, you've got to use energy to break the bonds to overcome the attraction. Describe how the motion of particles of pure Z changed from 0 minutes to 2 minutes. So from 0 minutes to 2 minutes, because you're adding energy into the solid, the kinetic energy is increasing. So number one, you can say that it is vibrating about its own fixed positions. That's for the first mark. And for the second one, you need to say that it's increasing in the motion. So number one, it is vibrating about its fixed positions and the motion is increasing. Part E, the experiment was repeated using a solid sample of impure Z. Suggest the differences, if any, in the melting point and boiling point of the sample of impure Z compared to the sample of pure Z. Melting point and boiling point. F. A sample of pure Z was allowed to cool from 120 degrees Celsius to 20 degrees Celsius. The total time taken was 8 minutes. Starting from point X, sketch on the grid below how the temperature of the sample of pure Z changed between 0 minutes and 8 minutes. So you've got a blank grid, y-axis temperature measured in Celsius, and on the x-axis you've got time measured in minutes. Okay, so now we've got to write down the melting point and the boiling points of impure Z. So it says suggest the differences, if any, in the melting point and boiling point of the sample of impure Z compared to the sample of pure Z. So we've just done this just now. So the melting point will be decreasing slightly because it's impure. So the melting point will be lower than pure Z and the boiling point will be higher than pure Z. Now, to answer this question, okay, let me just repeat the question. A sample of pure Z was allowed to cool from 120 to 20 degrees. The total time taken was 8 minutes. Starting from point X, sketch on the grid below how the temperature of the sample of pure Z changed between 0 minutes and 8 minutes. So let's compare the first graph. So the first graph tells you what happens when you heat the solid. So we need to look at the reverse. So if we look at 8 minutes on the first graph, 8 minutes, if you go from 8 minutes on the x-axis, you go up to the graph and then where it hits the line, and that is about 180 degrees Celsius. But we need to start at 120 degrees. So that means that the gradient must be steeper in order for it to fit in the 8 minutes on the sketch. So you need to draw a steeper gradient from 120 degrees down up to 80 degrees because you know that the melting point is 80 degrees. So the melting point is 80 degrees. That means you need to do a horizontal line because that's where the change of state is. So where it's 80 degrees, you need to draw a horizontal line and then you've got to end up at 8 minutes and that has to be 20 degrees. So where it says 8 minutes, you've got to end up as 20. So first you need to have a negative slope. It has to be steeper than the first graph. When that reaches 80, you need to have a horizontal line and then it should take roughly about the same time as the first graph. So it would take about 3 minutes for it to be horizontal. and then after 3 minutes you need to draw a negative slope all the way up to 8 minutes, and that has to be 20 degrees.